Hi, welcome to this time series using R video. In this video, I will show you how to perform spectral analysis in R. Okay. Spectral analysis finds repeating patterns in time series data. It converts data from the time domain to the frequency domain based on the Fourier transform. Okay. Frequency is the cycle per unit time. Period is 1 over frequency. And spectral density shows how variations is distributed across frequencies. Okay. A periodic gram should display spectral density estimates. Peaks indicate strong cycles. And phase measures timing differences between cycles. And coherence measures frequency-specific association between two series. And it helps to identify seasonality, cycles, trends, and noise. So basically, spectral analysis is moving from time domain to frequency domain, where you can see a lot of interesting patterns about the periodic structure in the data. Okay. So we need the forecast and the lattice package, and we can generate the data with the trend and the seasons. So Y has a trend plus seasonal 2 plus weekly plus noise, and we force them into a time series data, and we can print them out. This summary statistics. Okay. So part 2 is the visualization. We can split the window, and then we use plot TS data, meaning equal to generate time series with multiple components. Blah, blah, blah here. So this is what the raw data look like. You have time, you have value, generate time series with multiple components. Okay. Remember, we have trend, seasonal, and seasonal 1, and the noise. So we use the function called STL, supports one fixed seasonal period only. For illustration, this decomposition uses a 10 observation period, so 1 time unit, but it does not recover the simulate 12, 6, and 2 and 7 unit periodicities. Okay. So here, let's just do it a very simple way, just STL, window equal to periodic, robust equal to true, and we just plot out this STL decomposition, single imposed seasonal period. Okay. So you can see the first one is the raw data, and then the next one is the seasonal, the third one is the trend, the last one is remainder. Okay, part 3 is now we're doing a spectral analysis. Before we do spectral analysis, we need to remove the linear trend so we can get the residuals and of the linear regression of the time series data against time, and then we can make it to become a time series object again. And then we can call them function spec.pgram. And this is the main function we use for a periodogram. So we can use TSD trend, span equal to null, no smoothing. Okay, taper equal to 0.1, D trend equal to false, D mean equal to true, log equal to yes, and this is tapered periodogram of D trend series, and they look like that. Okay. So there's no obvious uptrend or downtrend. Okay. And we can get the frequencies, get the specs, and then other parameters for the dominant frequency, dominant period, and we can plot out the frequency, dominant frequencies and period, and then they have spectral density there. All right, so fixed approximate period 12, 7, and 6 time units, finite sample resolution, and leakage can shift peak location slightly. So, and then next one, let's do Daniel smooth spectrum. So we are doing some smoothing. So here spans equal C35. Last one is null. So now we'll get taper equal to 0.1. Now this look like smoother, right? It's less wiggly. So this is the neo smooth spectral density using C3 and 5. We can also use for the AR autoregressive spectrum using the function spec.ar. And this is what it looks like. The AR spectral density estimation look even more smoother. Okay, so it's a parametric one. AutoRMR can still be useful for time domain modeling, but it does not directly supply spectral estimate via arima.sim. So here we can use the AutoRMR and seasonal equal to false, stepwise equal to false, and then we can print out that model, give you parameter estimates. All right, next one, let's do moving average spectral estimate. So we can look into the ASTSA package, MV-spec function. It's a moving average smooth spectrum, not multi-taper. Okay, and there's a stats.spec.pgram explicitly to avoid the namespace ambiguity. Okay, so we can use spec.pgram, and then we use dtrend span now equal to C55, taper 0.01, and now this is the more heavily smoothed. So this is the span parameters are different, so this is more heavily smooth. It becomes smoother. Okay. And true multi-taper estimation requires an appropriate package such as multi-taper or PSD example after installation. So I'm going to skip this. Okay. Let's go to compare spectral estimates. So first, let's split the screen. And now we do this just with no smoothing. This is the raw. And then we do smoothing 7.7. So this is the Daniel smooth the space. Little smoother, the less. So the raw has like two peaks. Here is only one peak. We can do the AR autoregressive using the U walker, and then this is what it look like. So it's actually even smoother. Okay, it's less, but there's more changes. I don't know. You'll see the graph, right? And we can plot the smooth, the freak, and the spec, and it looked like that. So you'll be the judge. So you can see different, spectral estimates there. Okay. And then we can go to frequency domain features. This is really interesting. First, we need to write a function called the bandpass filter. So this function we wrote, what it does is gonna select the high frequency or low frequency, and then plot them out. You can see, I think one of the exciting feature of this frequency domain analysis is we can we can visualize some high frequency data trend in the time series or some low frequency. So high frequency, here you can see the first one is original and the low frequency components. So low frequency is usually kind of for the slower and longer trend, like pattern. They follow the data closer. And then the second one, you have original high frequency component. So this is you have with each with the compared to the original, you have somewhere you have a little bit like a spike, mini spike there. You get the high frequency one. Okay, so these are with the high frequency, and then you have a remaining frequency component. Okay, so this is actually one of the most interesting thing the frequency domain analysis can show you. You have a low pass and high pass filter. You can filter out the low frequency signals versus high frequency signals, okay, which is very useful in many applications. Okay, next one, let's do cross-spectral analysis for two time series. First, we create a Y2, and then we detrend both to get X1, X2, and then we use spec.pgram. So that's the main engine for all the spec periodogram. So here we use the same function, but now we have C bind X1, X2, and we do some smoothing, C55, taper 0.2, detrend equal to false, demean equal to true, plot equal to false. And then we can extract the frequency of the cross-spec, and then we extract the coherence and the phase. Okay. Now we can print out The coherence look like that. And we can add a horizontal 0.8 line. Is descriptive only, not a valid significant test. Just give you some idea. There seems there's the one peak that exceeded 0.1, but this is not a hypothesis test. Okay, so you can also print out the frequency cross, look like that. Okay, this is the cross-spectral phase. Okay, so let's do some hypothesis tests. First one is the Fisher's G test. We can write a function, and then we can run the test, and you can look at there. You got a very small p-value. So for the Fisher test, the testing, there's no dominant frequencies. Okay, so here is highly rejected. Okay, so there is some peaks in the spectral analysis, high frequency, dominant frequency. Okay, so then you have the lone box test. Also apply to the D-trend theories. A strong deterministic trend or period signal will naturally reject the white noise. Okay, so let's look at these. And also it's a reject the null hypothesis, not the white noise. Okay. Okay, and then we can do windowed spectral analysis. So we can say specify window size 128, step size equals 32, and get starts. And then we can number of positive frequency returned by spec picogram for a window. So here we're using this TSD trended starts 1 plus window size minus 1. So this is going through the windows. Then we get free STFT, the first window specs. And then we do a loop and then get to the window points. And then we can plot the heat map. And you can see the window midpoints and the wax as the frequencies, cycles per the time unit. So it's not really uniform, homogeneous. So there's some heterogeneity there, indicating the spectral density is not like a uniform. Okay, that's quite a lot. Sorry, I have to rush. There's a lot of things, but you can see it's quite interesting once you go from time domain to frequency domain. You can see a lot of things more clearly, like the low pass versus high pass filter get you high frequency versus low frequency signals. Okay, thanks for watching. And again, I'll share these R codes I'll paste them into the comms window area. Later on, I'll move it to my GitHub gist accounts. Thanks for watching.